Hi. In this video we're going to talk about something called relative dating. It's one way that geologists can take a look at a piece of land and try to figure out the history of that land and what's happened in the Earth's past. So relative dating is finding out how old layers of the rock are compared to one another. So it's essentially finding the sequence of rock formation. It would be somewhat similar to finding out when different children in a family were born, in what order. So you may know somebody as the youngest or the oldest or the middle child, but you don't know what year they were born just knowing that information. So for example, I am the younger of two children. But knowing that information doesn't tell you whether I was born in 1975 or 1995. Neither, by the way. So it just tells you formation relative to other events or compared to other events, not the actual time. And there's a number of different principles and laws that we're going to use to figure that out. It's important to keep in mind, though, that we can't do this equally easily in all spots. So in places where we can see cross-sections of the Earth, such as in valleys, river-carved stream beds, uplifted mountains, even man-made structures like highway excavations, all of those things allow us to see the layers of the Earth. And if you were just to go out into a middle flat field, you could analyze the soil and make some determinations about what was in the soil and how the weathering that occurred to create the soil happened. But you wouldn't be able to get much past that. It's important that we remember the rock cycle and that there are three different types of rocks. The origin of all rocks is magma. Once upon a time, the Earth was a big sphere of magma, and the rock that we have all formed from magma that cooled. And so the origin of all rocks is igneous rocks. And of course, magma is coming from inside the Earth, and so magma typically comes from below. Of course, there are lava flows at volcanoes, but typically magma comes from below and gets pushed upwards. The surface processes create sedimentary rocks. So recall, sedimentary rocks form from pieces of other rocks that have weathered, sometimes eroded, and then formed new rocks through deposition. And so the processes that make sedimentary rocks happen at the surface. So typically we find sedimentary rocks in layers at the surface. Metamorphic rocks come from heat and pressure, and naturally those aren't found in sufficient quantities to cause metamorphism at the surface. So that is typically also we see something in deeper layers. When understanding relative dating, a good place to start is the law of superposition. Superposition means, super means above, position means to place, and so the law of superposition tells us that sedimentary rocks are placed on top of existing rocks. What that means is that the oldest rock is at the bottom and the newer rocks are built on top of that, so that we know that the stratum, or in other words, the layer that is on the top tends to be the youngest, and the strata underneath it tend to be older. A good analogy of this would be your laundry hamper. As you put clothes into it, the clothes that have been in there the longest tend to be at the bottom, and the clothes that you put on there most recently tend to be at the top of the pile. So why is this? Well, when we're talking about sedimentary rocks, we have to remember how sedimentary rocks form. Sedimentary rocks are broken down by the process of weathering. That happens at the surface. The sediment then gets deposited through erosion and then lack of erosion, deposition, and that leads to the formation of sedimentary rocks. All of those processes that are associated with it happen at the surface. And so the newest rock layers are formed from the processes that happen at the surface. Throughout this video, we're going to be using this diagram on the right. This is a cross-section of the Grand Canyon, because of course canyons are great places to see lots of layers of Earth. Here's what the real thing looks like. This cliff right here is this cliff, and so we can see that of these top layers, our youngest layer is the one at the very top, the Kanab Formation, and the oldest layers are down deeper and deeper into the canyon where the river is. The next principle we're going to talk about is the principle of horizontality. The principle of horizontality basically tells us that sediment is deposited horizontally. So if the rock strata are flat, in other words, if they are horizontal, then they have not been disturbed. And if they are at an angle, then something has happened to cause a disturbance. When we look at the Grand Canyon, we can see that most of the rocks that we see from above are horizontal, so these have not been disturbed through here. But as we go down there is an angled section, so we know that something happened to cause this section to angle upwards. We also know that when that event happened that caused the angling, these top layers weren't there. This is a picture from the Canadian Rockies, which were formed from uplift due to subduction. You'll notice that the layers that are there are at an angle. That tells us that they were pushed upwards. So I alluded to some of the things that can cause it. So plate tectonics is probably the biggest thing that leads to disturbance. Stress from plate tectonics leads to deformation, folding, and faulting. There are other things that can also cause rocks to become angled. So for example, compression from a great weight, like such as glaciers, or burial. So according to the principle of horizontality, stratum 5 has not been disturbed. So that has to have been created after the event that caused the disturbance, that angled strata 1 through 4. So according to the law of superposition, 1 is the oldest, 2 is on top of that, 3 is on top of that, and 4 is on top of that. So that's the order. 5 has to be the youngest because it's not yet angled. The next tool we have for relative dating is the principle of cross-cutting relationships. So the principle of cross-cutting relationship basically tells us that if there is something such as an intrusion, in this case it would be an igneous intrusion that is pushing through, if there is something that cuts through rock layers, then the thing that is cutting through the rock layers is younger than the rock layers that were there to be cut. A decent analogy would be if you imagine that you had a layered cake in front of you and you stuck your finger in it to taste it. It's far more likely for the hole that you poked to have been created after the layers than it is for the layers to have been formed around the hole. So, according to the principle of cross-cutting relationships, number 4 cuts across strata 1, 2, and 3. So number 4 had to exist before strata 1, 2, and 3 existed. So it is the 4th oldest. In the Grand Canyon, we see granite, which is an igneous rock, that's intruded into schist, which is a metamorphic rock. And so we know that the granite has to be younger than the schist. Why does this happen? Well, if you've got existing layers and rising magma pushes into existing rock layers, it's going to break the rock layers, leaving behind something like a dike that you see here of igneous rock surrounded by layered rock around it. We call it bedded. If it's a fault situation where the rock has been broken, then the layers on either side of the fault need to be there before it can break what's there. Another note when we talk about igneous intrusions is that often around an igneous intrusion, in other words, a chamber of magma underground, we often see metamorphism occurring because, of course, the magma is warm and it's pushing up into existing rock, creating a lot of pressure. And so what we call this contact metamorphism. That's when heat and pressure from the invading rocks changes the rock around it, the existing rock around it. On our diagrams, when we draw rock layers, the strata that has undergone metamorphism has these little fringe lines to it. So our igneous rock that's intruded is this layer here. It's cut through E and F. It cut through E and F and spilled out on top of it. And the rocks that were there already experienced metamorphism right around the edges of that. So we indicate that with those little lines. So on your diagram, you may want to take a moment and add those lines on our igneous intrusion. Notice in this diagram, stratum 5 does not have those lines, so stratum 5 had to happen after the igneous intrusion. Another way of knowing that stratum 5 happened after the igneous intrusion is that the igneous intrusion stops at stratum 5. Another tool we have to understand relative dating is an inclusion. Not intrusion with a T, but inclusion, meaning it's a fragment of rock that has been included into another layer. So rock A existed, pieces of it weathered and broke off, and then because it had already weathered when rock B was formed, it was included in rock B. So the rock that's been included existed while the rock that is including it formed, and so the inclusion has to be older than the layer around it. An analogy I've heard for this is kind of like making cookies. If you're going to make M&M cookies or chocolate chip cookies, you need to have the M&Ms and the chocolate chips made before you make the cookie. So because the M&Ms and the chocolate chips are included in the cookie, they existed first. The next important thing to understand about relative dating is unconformities. So before we can talk about unconformities, we need to talk about what it means to be a conformable. So what that means is that deposition has occurred without interruption. In other words, rocks weathered, deposited, and formed sedimentary rocks, and all of the rocks that have formed are still there. An unconformity is when there has been a break in the rock record. In other words, something happened, usually erosion, that led to the loss of that deposition. So that lost data, like I said, is usually erosion. It could be a big event, it could be a landslide, a mudslide, it could just be a bunch of soft rocks that were weathered before a new layer could form. And so it represents a break in the story. Imagine you're reading a book and a chapter gets ripped out. You can tell that the chapter's gone because there's a gap in the glue and the binding, but you don't know what happened there. Now, there's all kinds of unconformities, and I don't care a tremendous amount that you know the difference between them, just that they are all examples of unconformities, or in other words, of lost data. So an angular unconformity is when there is angled sedimentary rocks, and then an abrupt end, like you see here, and then layered horizontal rocks above it. The information that was lost, as indicated by this kind of zigzaggy crumpled line, means that there was some erosion that happened there that we don't see anymore. At Grand Canyon, we have an angular unconformity right there. You'll also notice that we have two things labeled disconformity. All that means is that there was an unconformity that was parallel to the rock layers. It's not particularly noteworthy, other than it's a little bit harder to notice. And primarily we'll see it because the border between the layers is a little bit more jagged. Our last type of unconformity is referred to a nonconformity. All that means is that the event happened from below. The igneous or the metamorphic rock pushed up into the existing layers, and the break in the rock record happened from below.